Okay, in this recording we are going to talk about curved mirrors. We are going to start by concave mirrors. Concave side in the silverware mirrors among these spoons is going to be this one. We'll see that later on. Okay, how do we get a mirror? Think of a sphere, and then you come and cut a section of it. Now, if the silvered side, the reflecting side, is going to be the inside side, then we have a concave mirror. That's what we have here. Now, if the silvered side or the reflecting side that we are going to use is the outer side, outside, then we have a convex mirror. Now, we define a few things. Now, whenever we have a mirror, we define as the principal axis just a line, an imaginary line that goes through the center of the mirror. So we can have a principal axis for both mirrors, either concave or convex. Now, the center of the mirror is going to be the center of the sphere here, the center of curvature of the mirror. Okay. And both of them are going to have the same center. The distance from mirror to center is going to be the radius of that sphere r. Call that the center of curvature. What's interesting, it is the center of the sphere. So for a convex mirror, the center of curvature is actually behind the mirror, behind where are we going to have the objects and light and everything. But for a concave mirror, the center is in the same position relative to the mirror as the object would be and as the light would be. That's an important thing, an important distinction. An organic chemistry student accidentally drops a glass marble into a silver nitrate mirror in solution, making the outside of the marble reflective, like this. What kind of mirror is this? So here the shiny surface is the outside. So it must be a convex mirror. Okay, now we start with the concave mirrors. With a little geometry that we are not going to do, for thin mirrors. Large mirrors, it gets a little more complicated. But for thin mirrors, parallel light beams are going to meet at the focus. And the focus is going to be half the radius of the mirror. Okay? So for concave mirrors, under the approximation where the radius of curvature is so big compared to the size of the mirror itself, the focal length, or the point where the mirror is going to focus parallel light beams, is going to be at r/2. At half the radius of the mirror. Now, in this graphic, we are showing light beams from the top. If we have light beams from the bottom, same thing, they are going to pass by the focus. Now, the little geometry will show you that when I hit the mirror like this with a parallel light beam, now, what's the perpendicular to the mirror? The perpendicular to the mirror is the radius. So it's going to be passing through the center there. Now, if this angle is the same as that angle, that makes this going to half the radius. Just a couple of things, or just the important thing, the distance from F, the focus of the mirror, to the mirror, we call it the focal length. and it is equal to r over 2. You have seen it different ways. You can use a spherical mirror to start a fire. You can use a spherical mirror to catch TV satellite channels. Okay, now in the case of starting a fire, what you are going to have to think of, you are going to need sunlight, and that sunlight is going to come from far away, so by the time it's going to reach the mirror, the light rays coming off from it are essentially parallel to each other, and you want them to focus on one point to light up that fire. Okay, so to be able to do that, it has to be a concave mirror. Now, and this distance has to be the focal length of the mirror, or the focus. Now, TV satellite channels is the same thing. We have the satellite far away, and we have our satellite dish acting as a mirror, and you'd like it to focus where you place your satellite detector there. Now, what's interesting is a concave mirror is going to focus parallel light beams at the focal point, but then if you start light at the focal point, once it is reflected off the mirror, it's going to be the opposite process. Angle of incidence is equal to angle of reflection, so the beam should come out parallel. So a way to create parallel light beams is to have your light source emitting the light at the focal point of the mirror. For convex mirrors, whenever we have light beams parallel to the principal axis, once they reach the mirror, they are going to reflect again according to the law of reflection. But in this case, they are not going to meet. But the reflected beams are going to look like they are coming from the focus behind the mirror. And again, we can find that out by using a little geometry, remembering that your normal is the radius, angle of incidence is equal to angle of reflection, and that's why you are going to get it here. Now, the distance from mirror to the focus is again going to be equal to r over 2, but to say that it is behind the mirror, we are going to include a minus sign, to say it's minus r over 2, to differentiate it from whatever is in front of the mirror here. So the beams are going to look like they are originating from the focus, even though they never meet in the focus. Before I do this, just a quick review. For both mirrors, what we call the focal length is going to be r over 2. It's going to be plus r over 2 for concave mirrors and minus r over 2 for convex mirrors. Okay, in here we are going to focus on how to form images from a concave mirror. And we'll do it later for a convex mirror. Now, what I have here in three cases, I have an object that's designated by an arrow. And this is the center of the mirror. I mean, the central point for the mirror. And this is the focus. Now, in this case, I placed an object further away than the center. Here, we placed it between the center and the focus. Here, we place it closer to the focus. And in each one of these cases, we drew a light beam going from the tip of the object all the way to the mirror. Now, what we have learned in the previous screens is that this beam is going to have to pass through the focus. And that's what we see here. The reflected beam is passing through the focus. So it is easy here and here. Now here it's a little more difficult. The focus is in this other side of the object. It's to the left of the object. No problem. All what we have to do is the reflected one, we make it go through the focus again. Now, that beam is going to look like it's coming from behind the mirror. Okay, but we'll get back to that later on. Okay, let's see this in an animated way with the simulations. Oops. Okay, so this is the beam. When we are far away, you see the image is in black, the object is in blue. And no matter how large the object, if it is upright or inverted, the reflected beam is going to always go to the focus. And then it's going to continue onward, and it's forming the image here. One beam does not really form an image. You need more than one beam. So we try to identify what happens to other light rays reflected off the tip. Now, for example, here we take a second light ray. In this case, this light ray is going to hit the center of the mirror because of the law of reflection, so it's going to be reflected with the same angle. Okay. Now that if we are in between, the same case. If we are in here, same case. Third case, is what if we have a beam passing by the focus to begin with? Now that's the opposite from what we had in here. When the beam was going parallel, it passes by the focus. So in here, the incoming beam passes by the focus, so the reflected should be parallel. And the same thing no matter where the object is. Okay, except for this one here. When we get closer to the focus, we don't do much. Okay, now this is the combination of all three beams. The parallel going through the focus, the one through the center reflected with the same angle, the one passing by the focus coming out parallel. So all three beams are meeting here, So they form an image there. Of course, there are more than just these three beams, but these are principal rays to help show us what happens. Now, here, the same story. You notice that the third one is not visible anymore, but you see our image. The third one would have been here and hitting the mirror and coming out this way. It was not visible because the mirror got too big. Was not large enough. Okay, there you see it. And then here. Now here, how is it going to happen? Parallel is going to look like coming out here. Center, center, and then the one through the focal point, you just extend the line. All these, they look like they were coming from here. So what does this mean? The light beams are actually meeting here, so they are forming an image. So actually, if I put a film here, I should be able to get an image on that film. Also, you notice that that image is actually upside down, inverted. And it is smaller than my object. Now, if I come here, the light beams are still meeting here. They are still forming a real image that we can have on a film, that we can see in person, we can put on a screen. It's a real image. It is again inverted, but now it is larger than the object. And if we go here, it's a different story. It's larger than the object, but guess what? It is not inverted anymore, it is upright. And it is behind the mirror, meaning it's not going to form. So it is actually just a virtual image. Light is going to come out here, looking like it's coming from here. But it never meets there. So it is a virtual image, and that's why it is drawn in green there instead of black like the real image. Okay? So I described the three principal rays. Now we are going to dot the eyes a little bit. We define DO as the distance from the object to the mirror. If this is my object, this is the mirror, DO is going to be the distance from object to the mirror. It is going to be positive whenever the object is in front of the mirror. And it is negative if it is behind the mirror. Now, it's difficult to imagine how can you put an object behind a mirror and it's going to form an image. We'll be able to see that in lab in 2 weeks, how you can do something like that. But anyway, positive if the object is in front of the mirror, and DO is negative if it is behind the mirror. Okay, now DI, what we call the image distance. It's going to be the distance from where the image is to where the mirror is. DI. Now it's going to be positive whenever the image is in. Okay, what am I trying to say here? Whenever the image is inverted, and in front of the mirror. And it's going to be negative whenever the image is upright and behind the mirror. The focal length is positive when the focus is in front of the mirror, and whenever the focus is behind, it is negative. Now this is, as we said, it's a concave mirror. This, we have seen these in play in the simulation where we just played. Now we saw this one, we didn't see this one. Now what's interesting is the relationship between DO and DI and F. It's a simple relationship. 1 over DO plus 1 over DI is equal 1 over F. It's a very simple relationship. What's more interesting, we'll see that we are going to be able to use that same expression for all types of curved mirrors. I just talked about concave. We'll be able to use it for convex, and then we'll be able to use it also for lenses, as long as we define everything correctly. Okay, I'll stop here and we'll pick it up in the next recording.